Okay, so drill number one, question number one, how many centimetres in a metre? Just jot down the answer. Number two, without the use of a calculator, work that out for me. Number three, I'm scribbling away like that here. Number three, the formula for the circle is area is pi r squared. Formula I expect actually you to remember, so hopefully you knew it already. But for this particular question, I'll give it to you. If the radius of this particular circle is 50 millimeters, then using a calculator, calculate the area to an appropriate accuracy. So you can use a calculator for this one. We'll discuss what I mean by appropriate accuracy afterwards. Number four, what's a half times 3/4? No calculators now for this one. And number five, round 12.36 to one significant figure. And number six, write that number in engineering notation. Number seven, you've got 11 pipes at £13.88 each. Estimate an answer to that, please. And then when you've done it, is your answer high or low? So nothing, don't write anything down. It's a mental problem. If you're tempted to write something down, you're making it too complicated. I want an estimate for the answer. Yeah, just write a number down and then say high or low. Yeah. Number 8, what's 3.9 kilovolts in engineering notation? Number 9, there's a formula to find the power, electric circuit, estimate the power, so don't use calculators for this one. Again, it's an estimation question. What's the power when the voltage is 3.9 kilovolts and the current is 2.14 milliamps? Beware units. And that's it, 9 questions. Okay, let's have a look at them. So, number 1, how many centimeters in a meter? 100. How many millimeters in a meter? 1,000. Okay, there, you need to know those figures. Number 2, it's this asking about this BIDMAS, BODMAS, whatever you call it, rule, you know, the order of operations. I've got to divide that answer that goes on the top of here by what goes on the bottom. So I'm dividing the top by the bottom. That's the final calculation I'm going to do. So what is the top? What's the order? Brackets first. Well, there's two sets of brackets, so it doesn't matter which order I do them in. 3 plus 1 is 4. 3 minus 1 is 2. So then I'm going to square that bracket. 2 squared is 4. Times 4 is 16. Plus 4 is 20. So the top is 20. Order is important here. Multiplication before subtraction. 6 minus 2 is 4. 20 divided by 4 is 5. So order of operations. Number 3, just knowledge of where buttons are on calculators and how to use a calculator. What would I key into the calculator to do this? So the area is, I'd hit the pi button. You've got a pi button on the calculator. Shift and then down at the bottom somewhere. 3.14, yeah, it's a good approximation, but you do have a pi button on the calculator. And right, well, when you do get your calculator, the radius, you're given the radius is 50 squared. So if you do that, what's the button you hit on there? The x squared button. So pi times 50 squared equals 50 squared, 2,500. You might get this as the answer, 2,500 pi, which is an exact answer. But if you want the decimal, then you need to be aware of the third decimal button. Third, S stands for third, which is another name for a fraction in fraction form, and D stands for decimal. So if you want a particular decimal answer, hit that button and you get 2,500 pi as a decimal. And so if you hit the fraction button and you get 2,500 pi as a decimal, what would you get? 7853.98. Unit? Yeah, but we're finding an area, so millimeters squared. Okay. The last point to make about that is, and this is something that those of you who spaces or recognizers will be aware of, I bang on about appropriate accuracy. So what we mean there is, if I look at, I do the calculation on the calculator, it gives me this, and it gives me as many decimal places as the screen will allow. But the accuracy is determined by the number you put in. So that could be to 1 or 2 significant figures maybe. So if your number you're putting in is only 1 or 2 significant figures, what accuracy can I give to the answer? The same, 1 or 2 significant figures. So, extra supplementary question, what's that to 2 significant figures? Again? You sure? Right, 7,900 square millimeters to 2 significant figures. If that's a 5, go up. 5 or more, you round up. Note the zeros must be there because you've got to hold the 7 in the thousands column and the 9 in the hundreds column. So to 2 significant figures. So the zeros at the end are not significant, they're just there to hold the place. So that would be an appropriate answer, not 7853.98, because we can't really give that accuracy. Okay, Alex, do you see that? Not all the lecturers will be focusing on this, but this is my job really, the maths of it. So in other lectures and other areas, you'll do a calculation, and you'll find all sorts of answers coming out. Okay, but really, as far as an engineer in an engineering situation is concerned, if I really want to know what the area of this thing is, if it's the area of the end of a piece of metal or something, and I've measured the diameter, or the radius rather, of this piece of metal with a ruler, and it comes to 50 millimeters, then if I'm going to carry on and work out anything else to do with this, like the density, the volume, etc., I really do need to keep in mind the accuracy. I can't be more accurate than this as the area of it. And so if you're then using that figure to then prove something else, maybe the cost of it or something like that, and somebody wants to know exactly how much is this thing going to cost, well, you can only give that amount of accuracy to it, for example. So it does become important in the real world. Half times 3/4. 3/8. Right, okay. Now, what do we do? Yeah. Yeah. 3 times 1 is 3. 2 times 4 is 8. When you multiply fractions, you just multiply top and multiply bottom. 3/8. Okay. Yeah. Okay, no, you don't do that. I think what you're confusing that with is trying to find the common denominator when you add. Yeah, we'll come to that. When you multiply across, you just multiply top and multiply bottom. We will come on to algebra, of course. Okay. Oops. X over 3, we don't use a multiplication symbol. X over 3 times y over 4. X and y are letters that represent numbers. So they're numbers, we just don't know what they are. So X could easily be 1 and Y could easily be 3. They could be the same number, but they don't have to be different, but they could be different. So we use different letters to represent them. So using this idea we've just done here, what do they turn out to be if we multiply them together? Right. Yeah. So in other words, the basic idea of what you do when you multiply fractions is crucial when you come to multiply algebraically, which is why I bang on about fractions. If you're not sure of fractions, then you're trying to apply that to algebra, all sorts of horrible things are going to start happening, aren't they? Okay? I'm moving along fairly quickly. Stop me if you want to expand or you're not sure about something. Rounding is a useful skill, especially to one-significant figures, because you use that when we estimate. So to one significant figure. There's the first significant figure. Here. So what is it? 10. Right. 10. So one significant figure. There's the significant figure. The zero is only there to hold that one in the correct column, in the tens column. There are questions in the textbook that talk about rounding and significant figures and estimating. So in the early chapters in the textbook, you can have a look at some of those if you're not sure. Likewise, there's questions on fractions and manipulated decimals and stuff like that. Engineering notation is something we use an awful lot in all the other units. We're talking about very large numbers, very small numbers, so we use engineering notation. Are you familiar with it? Answer. Right, that's in engineering notation. Okay? What we do is, if you just wait till you've written that down, and then we'll look at it using this magic pen thing. There's the decimal point before we start. It's always at the far right-hand side of a number. And I want to move it to a convenient place. Tommy's decided he's going to move it to there after the 6, in other words here. And so then what you do is you say, right, I've moved it to there. I've now got to times by 10 to get it back to there. So I times by 10 once, twice, 3 times, 4, 5, 6 times, and I'll get back to where it should be. What's another way of writing multiplied by 10 6 times? 10 times 10 times 10 to the power 6, in other words. So that is actually equal to that. 136 million equals 136 times 10 to the 6. We say that's in engineering notation. What makes it engineering notation is this number. This must be a multiple of 3 for it to be an engineering notation. So I could have shifted the decimal point somewhere else and it would still have been an engineering notation. Give me another option. Somebody else apart from Tommy who did the first one. So what would I write down?
136 times 3.
No.
Oh yeah, yeah, big 3 zeros.
Right. Yeah. Okay. So now I've decided I'm going to move the decimal point to there. So I've only got to move it 3 places to get it back to where it should be. Right, Alex?
Why is it always multiples of 3?
Good question. The reason why it's always multiples of 3 is because it lends itself to prefixes like milli, 10 to the minus 3, mega, 10 to the 6. They always go in 3s, don't they? So it matches that, really. So 10 to the 6 is mega, so I could write 136 mega, whatever it is we're talking about.
Would it be correct also to do, as Tom said, 0.136?
Yeah, that's another example. It could also be 0.136 times 10 to the 9. Yeah, that's right. So that means I've moved it to here, and now I've got to go 1, 2, 3, 4, 5, 6, 7, 8, 9 to get it back. And that's the way it works for big numbers. For small numbers, what about 15, 18. That's roughly the charge on one electron. 196. Okay. If I've done it right, we'll find out in a minute. So, what would that be?
If you went over, yeah, it is 21 actually, yeah.
Is it 21? How do we check? I've moved it from there to here. So now I'm not multiplying by 10 to get it where it should be, I'm dividing by 10. And as we'll see when we look at the laws of indices, divide by 10 is the same as finding a tenth, which is to the minus. 10 to the minus 1 is a 10. So minus, so going back 1, 2, 3, 4, 5, 6, 9, 12, 15, 18, 21, 10 to the minus 21. You'll also see this is in engineering notation because it's a multiple of 3. But or we could write 1.96. And that's what's called standard form, when we always move the decimal point to after the first significant figure. So that will be 1.96 times 10 to what? The minus
20. Yeah. No, you're going back to 19.
And I had done it correctly because that's roughly the charge on one electron. 1.96 times 10 to the minus 19 coulombs. is the charge on one electron. So you wouldn't want to write the charge in one electron like that. You would write it either in standard form, and if you're doing a science course, I'd recommend you wrote it in standard form. But as you're engineers, you'd use engineering notation, you might write it like that, okay? Or 0.196 times 10 to the minus 18. So this is called standard form. And there is a section in the textbook, chapter 2 somewhere, I think, that talks about engineering notation in standard form. So have a look at it if it's a new sort of thing to you, or it's a while since you've done it. Okay. Number 7, estimation. When we estimate, we tend to estimate by going to one significant figure. If I were doing this, I would go 10 times 14 pounds. Yeah, I mean, actually, that's two significant figures. I'd probably go to 14. So what did we come up with as an answer? Yeah, 10 14 is 140 plus another one is 154. That's what I would have done, I expect. Exact amount in your head? Well, if you can do it in your head, very good. But most of us in a pressure situation, when you want to come up with a quick answer, would just want an estimate. High or low? Yes, a little bit high because we've gone up to 14 pounds, haven't we? Useful thing to be able to do for an engineer, because you're often banging numbers into a calculator, and if there's the answer and write it down, and the number of times you do it without thinking, does that make any sense? Really, you should be. How do you know it makes sense? Only if you've got a rough idea in your head what you're expecting to get. And estimating is one way to do that. So now we know how to get this into engineering notation. So at the back, you are. Right, I was going to guess that, but anyway. So what would that be in engineering notation? Because kilo is 1,000 or 10 to the 3. Yeah. We have these prefixes. Pardon? Right, okay, well, in the textbook or on your thing, you can have a look, yeah. We've got the prefixes that go with it. The most common prefixes, might be worth just jotting these down if you're not aware of them, but I'm sure some of you are. Kilo is 10 to the 3, which is 1,000. Mega is 10 to the 6, which is 1,000,000. Next one up. Giga, which is 10 to the 9. Let's not bother going any higher than that. Tera. Yeah, I suppose it is in computers. Yeah, terabytes nowadays is 1,000 gigabytes, 10 to the 12. Milli, 10 to the minus 3. Well, don't worry about those. No, just stick to the 3s. Milli, 10 to the minus 3. 1,000th, in other words. Micro. There's the symbol for micro.
Wouldn't deci be minus 3? Milli would be minus 6, wouldn't it?
No. Milli is minus 3, 1,000th. Deci is 100th.
Oh, yeah.
Oh, no, sorry, a 10th. Deci, a 10th. But that's a very uncommon unit, the decimeter. Millimeter, 1,000th of a meter. Micrometer is 1,000,000th of a meter, 10 to the minus 6. Below that is a nano, 10 to the minus 9. Below that, pico, 10 to the minus 12. We won't often go very below that. So if you're not used to the words, that's milli, that's micro, that's nano, and that's pico. And mega, and giga, and kilo to complete the picture. So those are the common prefixes, and again there's a chapter on that in the textbook. And I think you can see now how, engineering notation fits with it because they're all in threes. Happy with that? Can I move on? Nothing, so presume you're right. Right, another formula I'm going to be expecting you to know, power formula. You use that an awful lot of electricity, so know it, volts times current if you didn't know it already. Estimate the power when the voltage is that and the current is that. Oh, there was a 10. Oh no, there wasn't. Estimate the power when voltage is that and current is that. 8, yeah, it's just 8, isn't it? Because the kilo and the milli cancel each other out effectively. One's 1,000 and one's 1,000, so they cancel each other out. 4, rounding to one significant figure. 4, just wrote the answer down. 4, 2, 4 twos are 8, so 8 watts. Well done, Alex. 8 watts is an estimate for that answer. That's 600 notation. Now, if I wanted you to do that on a calculator, I would expect you to have a rough idea what answer that would be before you did it. By estimating, a bit like we just did for that one. So I round that to 4. I round that to 1. So the answer is going to be roughly 4. This is times 10 to the 6. This is times 10 to the 3. And as we'll see, when you multiply, you add the powers. So 6 plus 3 is 9, I would expect. So now when I do it on the calculator, I'm going to expect some number around about the 4 mark and the power of roughly 10 to the 9. Useful to be able to have an idea what to expect. I don't often worry about this too much, but I always add up these powers in my head and then I look at the calculator. Of course, if I do 8 times 5, I'm going to get 5 8s of 40 times 10 to the 9. So the calculator might give me 4 times 10 to the 8 rather than 40 times 10 to the 4 times 10 to the 10 rather than 4 times 10 to the 9. I've got it the right way around. But anyway, so you might find the powers one either side of that, but it will be roughly that. Just as a little extra question, do that on your calculator, please, and see what you get. So the main aim of today then is rearranging formulae that I want to spend some time on. I want to have a go at a few and then allow you a chance to practice some. And I'll put on the board some for you to have a go at, okay? Taken from the textbook, so that when you get the textbook, you can carry on with them. If there's one thing you're going to do as an engineer, it's that and you apply the maths that you've been learning, it's going to be using formulae and rearranging formulae. Generally using them, because then what happens is somebody has gone to the trouble of rearranging the formula for you and giving you the formula in the right form. What you're going to learn is how to do that job, okay, so that you can then give the formula to someone else. You can be the chief engineer who's saying, look, this is the formula you need, now go away and put the numbers in and work out an answer for me. Do you know that formula? That's not what that says there. Voltage equals times, because they're next to each other, multiply. So the first thing to say is about this formula, it's Ohm's law for start off. That's what I was sort of expecting you to say. Ohm's Law. I expect you to know Ohm's Law. You knew Ohm's Law, didn't you, Alex?
Yeah.
Yeah. It's a recipe. I often think of them like recipes. It's telling me what I've got to do to get the voltage. Why is it telling me what I've got to do to get the voltage? Because this is the subject of the formula. Okay? So the subject is generally on the left. That's what it's been set up to find, the voltage. How do I find the voltage? I need the current and the resistance. If I know the current and the resistance, I can find the voltage. What do? Multiply them together. No symbol between the letters means multiply. So, this is the subject, and no symbol, multiply. Using a little abbreviation for multiply. Hopefully you knew that. If, though, I want to make the current the subject of the formula, in other words, I don't want the voltage, I want the current, this is a very, very straightforward formula to rearrange, so it's a good one to start with. Rearrange for I, or make I the subject, straightforward. You might think, I know that, and then switch off. But what I want you to do, though, is to focus on it for a minute. Because the principles I'm going to talk about now apply to all. So although this is quite straightforward and you might think you know it, watch what's going to happen now, okay? I want to make I the subject. That means I want I on its own. I want this to be just I. So I want to get rid of the R. I want to get rid of what else is on the right-hand side of this equation. Sorry, this formula. So what I do is I use the fact that because of this equals sign here, it means the left-hand side equals the right-hand side. And it's true that I can add anything I like to that side so long as I add it to the other side. No, add it to the other side. Sorry. Whatever I do to one must do to the other to keep it balanced effectively. If I were to subtract a number, remember I'm putting symbols here but they represent numbers. If I were to subtract a number from that side, what have I got to do to the other side? Take it away. Minus k. Or, minus k from the other side. I've got to subtract it from both sides. If I multiply the right-hand side by something, what do I do to this side? Right. Whatever I do to one side, do to the same to the other. I can use that. I want to get rid of R. So I has been multiplied by R. So how do I get rid of it? Divide by R. If I divide that right-hand side by R, R's cancel. And I'm left with just I. So what do I do to the left-hand side? Divide by R. And so now I can write V over R, therefore, equals I. V over I because I. Generally, you're right, Tom, you put the subject on the left. So finally, I'd write I equals V over R. And I've rearranged that formula to come up with a new formula to find the current. Quite a straightforward example, but the principle applies to all. Rearrange for V. What do you reckon, Alex? Okay. Unlucky. It's not times. P over I. Look at this. What have I got to do to not take away? Yeah, if I divide the right-hand side by I, Alex, then I can cancel them. And so now what do I do to the other side? Divide by I. So V, and now the i's cancel, and therefore V equals P over I. Or V equals P over I. Okay? Another way of thinking about the same problem, this is the same working, but another way to think about it. Let's have a look at that. I don't know whether this will help. P equals VI. I want to end up with a formula for V. So I ask myself the question. What's happened to V to get the right-hand side? Alex, answer. What has happened to V to get what's on the right-hand side? What have I done? Times it by I. Haven't I? So to get rid of it, do the opposite. Yeah, to get rid of times by I. Times by I. So to get rid or undo this, divide by I. That's another way of thinking about it, but the overall effect is the same thing. If I divide by I, I must divide the other side by I. So in other words, I divide both sides by I, and that gets rid of the times by I, and so that would just be here's another formula. It's a formula to find the pressure in a liquid or the atmosphere. Three symbols there, H, rho, G. I just poured. Right. Remember what we've got here. We've got a recipe to find P. P stands for the pressure. So to find the pressure, I need three things, that, and that. And what are these things? Well, H represents the height or depth in the liquid. Whoops, depth. I won't bother putting in the units at the moment because we're just thinking about the formula. This symbol here might be a new one. Curly, looks like a curly P. It's part of the Greek alphabet and it's pronounced rho and spelled R-H-O. Rho. And in this context, it's used to represent the density. So if you think about it, the pressure in the liquid is going to depend on how far down in it you are and also the density of the stuff you're in. And
when you're in physics, you use D for density.
Interchangeable D and rho, I've seen both used. And finally, G is the gravitational constant. Not the gravitational constant, gravity on the Earth, which is about 9.81 newtons per kilogram. So you would look that up in the text. It's a constant. It's the force of gravity acting on each kilogram of mass on the Earth. That always stays the same, yeah. So if I know those three things, H, rho and G, what's this recipe telling me to do with them? Multiply them together. No symbol means multiply. So if I know H, and I know rho, and I know G, I just times them all together and I've got the pressure. Now what I want to do, though, is to rearrange this formula for H. So I'll just pause for a second while you think about what you might do. Let's look at it. Okay, again, we're not thinking about the answer, let's just focus on this for a sec. And think about it in the context of what we did on the last slide, which is what's the story, what's happened to the voltage in that case. What's the story, what's happened to H to get the right hand side? Right, to get rid of it. But what has happened to H to get the right hand side? Of times by rho G. Okay, so what do I do to get rid of it? Divide by rho G. Yeah. Yes. Yeah. You're jumping ahead, but yeah. That's okay, and you're ahead of the game. That's always good, okay? But what am I doing here? What's happened to h? It's been multiplied by rho g, so divide by rho g. Divide both sides by rho g. So in other words, p.
Rho G cancels out that also.
Yeah. Divide the left-hand side by rho g. Divide the right-hand side by rho g. That means g's cancel and rho's cancel, and you're left with h equals p over rho g. And again, you may want to miss out this intermediate step, but obviously you're then going to put the subject on the left. So h equals p over rho g is what you'd actually write. I'm just trying to keep the thing going down so you can see what's happening. Okay? Okay. Let's look at something a little bit more complex. I'll just pause while you write that down. So, just to repeat, because for the video, here's this formula. T equals 1 over 2 pi root L over G, where T is a period and so on. What's the story for L? We're trying to isolate L. We're trying to rearrange this formula so it reads L equals something for the subject of the formula. So I asked myself the story. What's happened to L looking at the right-hand side? It's been divided by G. Then it's been square rooted. And then after it's been square rooted, looking at this 1 over 2 pi, what's happened about that? Well, if we look at this aside that was written down here, finding a third of something is the same as dividing by 3. So in the same way, finding a fifth of x is the same as x divided by 5. Finding 1 over 2 pi times x is the same as dividing x by 2 pi. So whenever you see 1 over 2 pi or 1 over something, you could think of it as divide by it, and that will really help when rearranging formulae. So what's finally happened to it when we get to this bit here, I've divided by 2 pi, this step here. So to get back to L, I go through this process in reverse. I multiply by 2 pi, I square, and then I times by G. I do the opposite to go back. And then I should end up with a formula for L. Another way to write it, and I'm going to look at this on the other side here. If you think about this, let me write the formula at the top, so we've got it to refer to. Root L over G. Now, I'm going to generate this right-hand side. So I'm going to start off with L. As a reminder, without looking at the notes you've just been taking, what's the first thing I'm going to do? Times by G, and I get to L over G. So did you say times by G? Divide by G. To generate it, I divide by G. And what did that? Divide by G. To get L over G. And then I want to end up with this right-hand side, Denzel. So divided by G, and then I square root. Yeah. Square root to get the square root of L over G. And then finally, I divide by 2 pi. To get note this step, root L over G over 2 pi, which is a very cumbersome way of writing a formula, which is why we tend to write 1 over 2 pi times root L over G. That's why I write it in that form and not like that, because it looks awkward like that. But the best way to think about the process of undoing it is to think of it in terms of divide by 2 pi. Okay? So that's generated the formula, 1 over 2 pi times root L over G. Now what I do is I go backwards. So I start off with the root 1 over 2 pi root L over G. And now I'm going to go backwards. So look at this. Multiplied by 2 pi. And what does this equal? It equals t. So I'm going to multiply by 2 pi, and that will undo the divide by 2 pi. So I'm left with multiplying by 2 pi, I'm left with root L over G equals t times, okay, yeah, t times 2 pi. Let's write the 2 pi first. 2 pi t, doesn't matter what order I write it in. Now I undo divide by, I've done that, I undo square root by squaring, so I square both sides. And I get L over G equals 2 pi t squared. Square both sides. And finally, multiplied by G. And L equals G times 2 pi t squared. I've got a new recipe to find the length. I'll just pause while you write that down. Just look again at it. Let's look again at this formula. And what do you do? Remember, we're identifying the steps. All you're really keen, interested in is what was the last thing that happened. So you go through the process, but what's the last thing? Well, it was divided by G, then it was square root, blah, blah. The last thing that happened was it was divided by 2 pi. So you undo that step. And so I'm going to multiply by 2 pi. I might write that down by the side, what I'm going to do, but probably not after we've done a few. And so then I just say, right, I've rearranged it by going 2 pi t equals root L over G. I multiply both sides by 2 pi, and that gives me to that. Yeah, so the green is sort of how you might think of it. So it's divided by 2 pi, so multiplied by 2 pi. That gets rid of that. And now I look at it and say, right, if I look at it now, the last thing that happened on the right hand side was square rooting. So square to get rid of that. Square both sides. Square both sides. So how do I show this on the left hand side? I rewrite what's on the left hand side and I square it. And then finally, to get back to L, how do I get rid of the divide by G? Multiply by G. So it's a 3-step process to rearrange this formula. So G times 2 pi t squared equals L. Or writing the subject first. And I've got a new formula, a new recipe to find the length of the pendulum. If I want a particular length, then I can put in the values. if I want a particular period, say of 3 seconds, then I can plug it into this formula and find out what length is required to give me that period. I could do that, couldn't I? Because I know what 2 squared is, it's 4. So I could take that outside the bracket and just call it a 4. You might well see the formula written like that. And at this point, if you all had calculators, I'll give you some numbers to work out the length, and we'll perhaps do that sort of thing next week, okay? Because that's equally important. That's one of the equations in motion for a body that's moving. V standing for final velocity, U for initial velocity, A for acceleration, and T for time. Some of you may have seen that. Particularly you've done the BTEC course. You probably did that, did you?
Yeah.
V equals U plus AT. So V final velocity U initial velocity A acceleration T time. Very common formula if you're looking at mechanics motion. Sorry? Well, no, not initially. I'm going to have a look at a couple of things in this. If I wanted to rearrange this formula for U, look at it, what's happened to U? What have I got to do? What have I got to get rid of? I've got to get rid of the AT, so I subtract it, yeah. So if I subtract it from the right-hand side, I must also... So I write that. So if I want to rearrange for U, I write V minus AT equals U. So U equals V minus AT. Done. What about if I want to rearrange this formula for A? Now we've got to be a little bit careful, Tom, because we've got a combination of multiplies and additions. So the big mass thing comes in. Now it's worth thinking of the story. What was the last thing that happened to the right-hand side in building this up? No. What was the last thing you do? If I start with A, what was the first thing that happened? Multiplied by? Right, if you look at just building up this right-hand side, if I start with A, to build up the right-hand side, and this is the sort of logic of it really, start with A, the first thing I do is multiply by T to get AT. And then I add U to get U plus AT. Okay, that must be the order. If I start with A and the first thing I do is add U, I'd get, start off with A and add U, I would get A plus U. And then if I multiply by T, I'd get T multiplied by A plus U. Not that, wouldn't I? So that would be wrong. Do you see how the order is so crucial? No. The order that's happened to A is, first thing I did was multiply by T, and then I've added U. The key thing I'm after is, what's the last thing that happened? Added U. So what's the first thing I get rid of? The U. Okay? I get rid of the last thing first. It's like working your way back to the middle of the onion in a way. So you've got to, that's where the logic comes in, and that's where the mathematical mind comes in. What was the last thing out to the right hand side? U was added. So therefore, subtract U. So I subtract U, and I get V minus U equals AT. Now I divide by T. Okay? So V minus U over T equals A. And that's the formula. A equals V minus U over T. Just pause a sec. A little aside, I'm going to talk now about why it is you've got to do the minus U first and not divide by T. And look at the consequence if you divide by T first, okay?
T would be pretty much the same as A and T trace on the divide by.
Say that again.
We got A there, but to get T, do the same, but we'll obviously say.
Yes, you would. That's correct. Yeah, that's right. But if in this first one, do you remember we were after getting A on its own?
Yeah.
If you had have divided by T first, what would have been the consequence of that? Why wouldn't it have been worked? Why wouldn't it have worked? Let's have a look at it. And so there's a little aside here. Okay, that's true, isn't it? And I now want to divide both sides by 2. Remember I said, so long as you do the same thing to both sides, it can't matter. What have I got to do, though, to divide both sides by 2? For it to still be equal. Divide this side by 2, I get 3. Yeah, I've got to divide both of these things by 2 for it to work, haven't I? So in other words, if I divide both sides by 2, I've got to divide every term on both sides by 2. And it gives the same answer, yes.
So, I mean, whether you do, whether you add up 2 times 4 and divide by 2, or whether you divide 2.
That's true, yeah. But algebraically, let's look at the consequence here. If I've got V equals U plus AT, and the first thing I do is divide by T, what have I got to write?
You divide by T equals U.
No. In terms of what we've just been doing here?
You divide by 2 plus A.
Right. The T's gone from that. That's what we wanted, isn't it? But I've got to divide every term by T. Now I subtract both sides. I subtract U over T from both sides. So I get V over T minus U over T equals A. And as Tommy's indicating, and when we come to look at addition of fractions, we can add or subtract fractions if the denominator is the same. So because it's both T, I can write same answer. Same answer. But a bit more complicated. And so always try and get rid of the last thing first. But however, the point is reinforced. It doesn't matter what you do to a formula, so long as you do the same thing to both sides, it can't be wrong. But it can be more complicated if you try and do the wrong thing first. But you will end up with the same answer eventually. Okay? I've done a lot of algebra and rearranging formulae. Any comments? Backbench, first tell me something you've learned today about rearranging formulae. Reverse the process, right. To rearrange, yeah. Would you like to add to that? What do you mean? Can you expand on that a bit?
So what we did last was
Right. Undo what you did last. What's going to go at the end of that? What word would be good to go in there? Anybody help him out? Undo what you did last. First. Thank you, Denzel. In rearranging a formulae, undo what you did last first. Thanks. Middle bench.
If the two bottoms of the fraction are the same, put together.
Okay. So if denominators are the same, you can put together. Yeah, that's a good thing to remember. In other words, so thinking of that example, Denzel, we're looking at, V over T minus A, was it U over, I can't remember now, U over T equals V minus U over T. Yes, you can put them together, that's what he meant, wasn't it, Denzel? Front. Right. Whatever you do the one side, you do the same, if I can add that, Tom, to the other. But that's what you meant, isn't it? Not the opposite, the same. Anything else? Anybody? To take out of this session?
Is all this you're doing right now being the end?
Yeah, I'm recording it, hopefully. Yeah, I am. So yeah, I'll put it on the website.
What was that? You know that's 2 pi.
Yeah.
That's
Oh yeah. Yeah. So multiplying by 1 over 2 pi is the same as. Yes, thanks for that. That's good. Dividing by 2 pi. Yeah. And of course, it works for anything, not just 2 pi. Multiplying by 1 over something is the same as dividing by it. Yeah. Worth remembering, especially when you're trying to undo things. Anything else? That's a good list. I can't think of anything in particular, but you might. That was new to you, or that you thought, ah, that's good. Right, engineering notation, yes. So generally, general points, yes. Use engineering notation. So if you're not clear on engineering notation, it's something you have not done before or it's a long while ago, check that out in the textbook when you get it. Here are general points. Yeah. Remember to bring a calculator, piece of paper. Okay. Okay, just to bring this to a close then, having this chapter 10 in the textbook on transposition of formulae goes through some of the things I've been talking about, introduces the idea of what you do to one side you must do to the other. Like all the chapters in here, it gives not much information, but lots of work problems. Transpose A equals F over M for M. Work problems, 6 work problems, 7, so therefore there must have been 5 beforehand. Lots of work problems, followed by exercises. So exercise 39, transpose these formula. Transpose number 2, x plus 3y equals t for y, and so on. Okay? There's a solution. So you know you got it right when you've done it, but you need to be clear on the steps. I don't think it's a problem of the solution being there, apart from the really straightforward ones. But you still need to work through the steps and check you understand what's going on. I've done some video links for these, so again, if you get stuck on one of them, have a look at the video clip, okay? I've really done the second or third session before the first one because I was hoping to just do, using form was probably a bit more straightforward. So you've jumped right into some quite awkward stuff. So, you need to just take time and think about it and absorb what we've been doing today and try some of these questions. Okay. If you want to go ahead and look at some of the stuff we're doing next week, we're going to go back and looking at evaluating formulae, putting the numbers in standard form and engineering notation, talking about errors like we did with significant figures and stuff like that. And if while we're at it, if I can bring your attention to standard form, chapter 2, earlier parts in chapter 2, it talks about what standard form is, 2.4, and engineering notation is, and indices, standard form, and engineering notation. So look at chapter 2. There's also calculator practice in here, in this particular chapter, how to put numbers into the calculator and so on. So the early chapters are useful to get you up to speed. Yeah, if you get a chance. And next time I see you, we'll spend some time on that. So that's a little preview of what's coming. Okay? Right.